this, and this time I finally remembered. Here we go. Okay, so in number 17, we are comparing two watermelons. Watermelon number 1 is going to fall, and it's going to land on a nice soft pillow. Watermelon number 2 is going to land on the cement. All right? And the idea is, in both cases, our watermelon is falling down with an initial velocity of 12 meters a second, right? But you got to make it negative because it's going down, right? Okay, and that same thing is going to be true over here for the watermelon that lands on the cement. Good? Because they're both being dropped from the same height. Okay? Now, regardless of whether the watermelon lands on the pillow or on the cement, it's going to stop. So both objects have the same final velocity. Yes? All right. The problem also tells us that the watermelon has a mass of 8 kilograms. That obviously is not dependent on what it is landing on, right? Cool? So because of this, notice, remember, change in momentum is mass times Vf minus Vi, right? Our velocity is changing, which means our momentum is changing. So we're going to get 8 kilograms times, let's see, 0 minus negative 12 gives us 12. So you get 96 kilogram meters per second. So that's true for the one landing on the pillow, right? Okay, that is the change in momentum, also known as impulse, yes? All right. What about the one on the cement? How's it going to be different? Or is it going to be different? It's not going to be different, right? Because it's going from the same velocity to the same ending velocity, right? So it's losing the same amount of momentum. So in English, both, I don't know why I'm writing this in red, both times, whether it lands on the pillow or on the cement, you're going to have the same impulse. You're going to have the same change in momentum. Cool? Does that all make sense? All right, so where's the difference? Well, the difference is this. The pillow, because it's soft, it sort of has more give to it, like give, right? So the idea is when the pillow hits when the watermelon hits the cement, it's going to fall and stop in a teeny fraction of a second, right? Whereas when it hits the pillow, because the pillow has a little bit of give to it, it doesn't just hit it and stop, it hits it and poof, kind of sinks into it a little bit, right? And that process of sinking into the pillow allows more time for this change in momentum to occur. Okay? So, look. The problem told us that the one landing on the pillow takes half of a second to stop, whereas the watermelon landing on the cement takes 0.005 seconds to stop. In other words, this one stops almost instantaneously, and this one stops very quickly, but not nearly as quick as the one hitting the cement. Follow? All right, so look. If change in momentum is net force times time, that means that time is change in momentum. No, that's not what I'm going to do. Sorry. How about if I do it the right way instead of the wrong way? You guys will learn more that way. Net force is change in momentum over time, right? So on this side, the one landing in the pillow, my change in momentum is 96. But that change in momentum only takes half of a second. And so the net force required is 96 divided by a half gives you 192 newtons. Follow? Whereas over here, change in momentum is net force times time. That means that net force is change in momentum over time. So we need the same change in momentum, but it takes 1/100th of the time. And therefore we have 100 times as much force. Does that make sense, you guys? You're dividing by less time, and so it's going to take more force to create the same change, right? Follow? All right. So this was on your worksheet. Sorry, I totally did this out of order. This is question A, and this is question C, right? Because both of those questions ask you for the net force on the watermelon. Good? So to me, this is the important part. Are there any questions on what I did here? We're good? Okay, so real quick, let me walk you through how you do B and D. So what we just found is the net force. So here's my watermelon. We just found our net force. So like in the first part, it was 192 newtons, right? Question B says, how much force does the pillow exert? So what forces act on the watermelon? Gravity. So let's see, it's an 8 kilogram watermelon. So my force of gravity is going to be 8 times 9.8, which is negative 78.4 newtons. And what's the other force? The pillow. So now it's just net force equals net force, right? What force from the pillow plus this negative force of gravity gives us this net force. So you just solve for the missing force, and it turns out to be like 270 or something like that, 270.4, I think. Follow? All right, and then D is similar. All right, but so the big thing I want to make sure you guys understand is this. Both the pillow and the cement create the same change in momentum for the watermelon, right? The difference is, because the pillow has give, it allows more time to stop the watermelon, and therefore it takes less force to stop the watermelon. And the cement stops it very quickly, and as a result requires more force. Cool? Questions? Any problems? Okay, so this is going to be a question on your test when we get there at some point in the next 8 weeks after all the weirdness happens with scheduling and spring break and things. But I want you to explain the why, okay? Which particularly I find honors students struggle with. Because I think you guys are so, for many of you, your strength is plugging numbers into equations and getting answers, right? But then explaining is a little tough. All right? So in your note packet, you've got a page that looks like, I've got a gajillion blank pages in here, like this. All right? It says decreasing the force needed for a predetermined change in velocity, the airbag question. All right? There are a gazillion examples of this. All right? I always refer to it as the airbag question, but it's basically this. It's about what I'm going to call a safety feature. All right? In that last example, the pillow acted as a safety feature to keep the watermelon safe, right? Just like in a car accident, the airbag is a safety feature designed to keep the people in the car safe, right? All right? So the question is, why do they keep you safe? All right? So the operative thing, the thing that sets this apart from the other example we're going to talk about is this. Predetermined change in velocity. All right? Whether the watermelon hits the cement or a pillow, the velocity is going to go from whatever to 0, right? And you have no control over that, right? Okay? If you're driving in your car and you're in an accident, it's not like you go, I'm going to get into an accident. I'm going to slow down to 10 miles an hour before I hit this brick wall, right? You're just like, darn. Here comes another car, right? My velocity is going to suddenly change, right? Okay? So here is the deal. You should write this down. With or without a safety feature. Do you guys know what I mean? I'm speaking in generic terms here. Are you all cool with what I mean when I say safety feature? It's the pillow versus the cement, the airbag versus the steering wheel. We'll talk about some others in a minute. All right. So with or without a safety feature, the object will have the same change in velocity. In other words, your velocity has to go from whatever to usually 0, right? Follow? And therefore, I'm going to write thus because it's less letters. And thus, the same change in momentum. What's another way of saying change in momentum, you guys? Very good. Impulse. You need to equate those two things. Change in momentum is the same thing as impulse. All right, so that is one sentence. With or without a safety feature, the object will have the same change in velocity and therefore the same change in momentum, or the same impulse. We are halfway there. Pretty good? All right, so what's the whole point of the safety feature? What was the whole point of the pillow? How does it decrease the force? It has give, and so it allows more time for that change to occur, right? The safety feature allows more time for this change to occur. And once again, thus requires less force, which is the whole point. Right? When somebody punches you, it's the force that hurts you. That's why they always say it's not the fall that hurts, but the landing, right? The fall takes a long time, the landing, not so much. All right, this will be on your test. It is 4 points. I will show you where the 4 points are when you are done writing. I'm telling you it's on the test because I want you to know it. So just make sure you can explain it in these words or your own words. Ideally your own words, but I'll take it. All right? So here are the 4 points. You are going to get 1 point for simply telling me that whether you've got a safety feature or not, you're going to have the same change in velocity. That's 1 point. You have to establish the fact that's instrumental in setting up this argument. You got the same change in velocity either way. And that means that you're going to have the same change in momentum, or the same impulse. That's a point. If you skip this, then the rest of the argument doesn't work. Okay? Because the only reason more time means less force is because the change in momentum is fixed. Okay? So point number 3 is going to come from you telling me that there is more time for the change. And point number 4 comes from telling me that it requires less force. Cool. If you would like to summarize all of this, just for your own benefit, this would not be an acceptable answer on a test, but if you wanted to summarize this in very simple symbols, here's how we can do it. Safety, no safety. All right, in both cases, you've got the same mass, the same VF, and the same VI, and therefore the same change in momentum, right? The difference is the safety feature allows you a large amount of time and therefore less force. Whereas without the safety feature, you're going to stop really freaking quick, which requires a lot of force. Does that make sense? So this middle chunk is just saying this is the same on both sides. Right? Same mass, same VF, same VI. Cool. Questions, issues, concerns? All right. So I feel like I should show you an example of this. Are you prepared for examples, or do I need to give you a minute to finish word writing? All right. Let's do some examples. All right. Anybody ever been bungee jumping? Yeah? No? Nobody? It was a big thing in the 90s. The summer after my first year teaching in 90-something. What's that? Oh, right. That makes sense. Because because I did it when I was in my 20s and done. So the summer after my first year teaching, I went to this physics conference out in Oregon, and we all went out one night and went bungee jumping with data collection devices strapped to us because we're total nerds. Because it was a physics conference, right? So we measured our acceleration. It was super geeky. Anyway, it was fun. So I'm certainly not saying that you should try bungee jumping, because there are, anything like that, there are sort of inherent dangers. But I think, and correct me if I'm wrong, but I'm guessing that you would all say that bungee jumping is safer than chain jumping? All right, chain jumping is not a real thing. Why? So why is chain jumping a bad idea? I'm going to give everybody a second to think about it, and then I would like Lauren Tom to give me the best answer she can. What do you got?
There's no give in the chain, like there's no bungee cord.
Okay, and so...
It takes less time for you to stop.
Yeah. Do you guys agree? If you had a chain and a bungee cord that were the same length, by the time you get to the end of the cord, you're going to be going the same speed, right? And she's exactly right. That chain is no give, so it's going to stop you in a small amount of time, requiring a huge amount of force, right? Do you agree? The bungee cord's going to stop you eventually too, right? It just takes more time, right? All right, so let's see it. All right, so I've got this motion sensor set up over here. So you guys can see this yellow string here. This yellow string is going to represent our chain because it has no give to it. All right, and then I've also got this red one, which is like our bungee cord. It's got some stretch to it. Okay, so let's see this. Let's see. So the graph up there on the screen has two axes. There's a time axis and a force axis. The vertical axis is force. Horizontal axis is time. We need a passenger. It's Rick. All right. Okay. So here we go. Are we, any questions before we do this? All right. So let's go ahead and hit collect. Make sure everything's all. I think we're good. We're collecting. Here we go. Oh, we still have time. No, we don't. Oh, that was horrible. Oh, it got stuck. Darn it, same thing happened last hour. Well, I guess I could just go on the other side. Duh. All right, let's try that again, and this time we'll do it. All right, here we go. We're collecting data. Yes, is it going? It's going. Here we go. Ah, much better. All right, notice Rick didn't fall off until the cart ran over the bungee cord. Take a look at the graph. So there's not much to look at here. So basically, the force was 0, right? And then when we ran out of slack, what happened is the rubber band started pulling the force probe, okay? And the force got bigger and bigger and bigger. Hooke's law, right? As the stretch gets more, the force gets more, right? So here's our maximum force. That must be where it stopped. And then it uncompressed and the force got less. Good? All right. Now, if hypothetically this force had been constant, then we could simply do force times time and find our impulse, right? Okay. But the force isn't constant, so to find that, we'd have to use an integral. And if you take AP, we'll talk about that then. All right. So, questions? All right, so let's replace the bungee cord, the stretchy bungee cord, with the not so stretchy, quote unquote, chain. All right, how's the graph going to look different? Turn to your neighbor. Tell your neighbor how it's going to look different while I set this up. All right, are we ready? All right, let's try it. Here we go. Oh, darn it. I forgot to save the previous one so we can compare. We're doing this again. We're going to get this to work. Hold on. You guys are going to wait while I get this to work the way I want it to. Darn it. We're going back to the bungee cord. Sorry. You guys have to watch me be inept a little bit longer. Nope, I'm still recording. So people at home, they're just going to have to wait. Come to class. Then you can watch me be dumb live instead of All right, let's zero this thing. Let's experiment. Start collection. Is it going? It's going. Here we go. Once again, bungee cord. Hooray. Notice he didn't fall until I stopped him. Somebody in 1 second remind me to go click save data.
Click save data.
Oh, thanks, Tim.
You are so
Whoa, Tim, shut down. All right, here we go. Here we go. Experiment. Store latest run. Good, now we can compare, which was the whole point, right? Okay, everybody good? Here we go. We're back to the chain now. Here's the chain. Is it going? It's going. Here we go. I forgot to put Rick on. All right, so we'll put Rick on in a minute. What do you notice about the graph? Pretty big spike, right? Look, huge force, itty bitty time, right? Clear?
Yeah.
All right, and just so that I don't deprive you of the Rick experience.
Okay.
I think that's a thing. Isn't that an episode? Should be. Did you guys hear it didn't get renewed? All right, you ready? Here we go. Rick. Oh. All right. Questions? All right. In which case did the cart have the bigger impulse? With the bungee cord or with the chain? They're the same. Thank you. People always say that it's bigger with the chain. It's not. The impulse is the same. The change in momentum is the same, right? Good? Questions? All right, example number 2. So some of you got here early and may have seen that I was cleaning some goo up off of the floor. That's because I let a student throw an egg and said student missed the target. So I went to the grocery store yesterday and I purchased some eggs. They're cage-free. Because even though I eat meat, I still like my animals to be happy until I eat them. So cage-free eggs, all right? So hypothetically, if I was to throw this egg at that wall or hypothetically that table over there, what would happen to the egg?
It would break.
It would break because there's no safety feature. We should construct a safety feature for our egg. I need 4 volunteers whom I promised to not get egg on. 1, 2, 3, 4. Very good. Come on back. Hold that. All right. Let's see. So Tim and Joey, I think are probably taller. So I need you guys. You guys are going to be the upper end. So you're going to grab that. You're going to good solid grip on it. You grab that. You're going to get solid grip on it. Tom, grab that. You guys are up. You guys are
I'm like,
down. So we want the sheet to look like this, you guys. That's what we're going for. Cool? All right, and then I need you guys to move away from the table so that the egg doesn't hit the table. All right, everybody got it? All right, so you can relax. You're good. Like you don't need to be like, well, I don't, that relaxed. I just meant like you look like. Okay, so do you guys have good grips on it? Because the only time this ever doesn't work is if somebody lets go by accident. Good? Everybody good? You got a good grip? All right. Anybody on the baseball team? Drew, come on!
yeah, Drew.
All right, so what do you play? All right, I'm gonna just let you use. Do you think that you can safely hit see where this little hole is? Aim just to the right of it. Go for the hole. You can aim at the hole. Throw it as hard as you want. You're not gonna break it. Challenge. Just don't hit any people. Oh, come on. Throw it.
Like 2018, I can't say.
Line up. Don't. There we go. Oh. it hit the sheet. Hold on, I want to prove to you that this works. Try again. All right, let's get it. Let's do it again. All right, you guys ready?
Yeah.
Very good. Oh no! That's never happened ever. Did I grab the one in the front? What would it be? The left back?
Yeah.
All right.
He is. I want to spot that video.
I'm so frustrated. I opened this box for an hour and I started to grab that one and I was like, that one's cracked. I did not grab it. All right. Okay. Well, so Drew's first two throws were good. The second throw, I want you to be aware of. He threw it. You threw it pretty hard that second time, right? And it didn't break when it hit the sheet. When did it break? When it hit the ground, right? Which further proves the whole point, right? All right, so that's frustrating. I've been doing that for many years, and it's never broken when it hit the sheet. So, all right. Anyway, you guys get the point, right?
Yeah.
Questions? All right. Okay. Cool. All right. So I guess the last thing we need to talk about then is number 18. So number 18 is the one about following through, right? So real quick, tomorrow we're going to watch a quick video about car crashes so you can see the airbag thing in action. So it's not graphic. Maybe a little. No, it's not at all. It's like an old driver's training. I'm going to shut up now. Okay, so okay, so
Yes, you should have demonstrated.
what are you doing? All right, so let me walk through number 18 real quick. All right, I'm guessing I probably don't need to do the math on number 18. Okay, so but here's the deal with number 18. You guys have all, at some point in your life, been to some practice, either golf practice or soccer practice or baseball practice or something, and the coach is like, follow through when you hit the ball, right? Okay? And so the advantage of following through is this. All right, so here's the deal. When you follow through, so in the problem it says you hit a golf ball, it says you exert a force of 800 newtons, right? And then one time you follow through, one time you don't. What's the advantage of following through, you guys? More contact time, right? Does it change the force? No. It's not like, oh, I'm going to follow through, and you're suddenly stronger, right? Like, you can only exert as much force as you can exert, right? Okay? So, yes, you guys are exactly right. Following through allows that force to act for more time. So conceptually, it's this. Whether you follow through or not, you're going to be exerting the same amount of force, right? If you don't follow through, then that force only acts on the thing for a small amount of time. Whereas if you do follow through, it acts on it for a large amount of time, right? What does net force times time give us? Impulse, change in momentum, right? Oh, well, here I've got a force in a small time. That's going to give me a comparatively small change in momentum. Whereas over here, because this time is so big, I'm going to have a big change in momentum, right? Okay. In terms of equations, I always think of impulse equals force times time is the cause. Right? Like, how do you cause a change in momentum? Oh, well, you have to exert a force for some time, right? What's the effect? What's the result? What's the other equation? There's two equations for impulse. Force times time and
Mass
mass times change in velocity. That's the effect, right? So the result of this change in momentum is that my mass undergoes a change in velocity, right? Whereas over here, I've got the same mass undergoing a larger change in velocity, right? Does that make sense? Did you guys all figure out that the size of the letters represents the size of the numbers? Make that jump all right? All right. Good, you guys? Big time, big change in momentum, big change in velocity. All right? So let's write it in words. So, here's the deal. Before we write it in words, actually, so I just spent a whole bunch of time telling you that if you make the time bigger, you make the force smaller. Right? Wasn't that the whole point of the failed egg in the sheet experiment? Yes. Sort of, but that didn't happen here, right? Here, my time got bigger, but my force didn't change. Why? What's the difference? That's what I'm asking. Why is the force constant? Why didn't the force change? Why didn't making the time bigger make the force smaller? An idea?
Is it? No, never.
How is this example, following through when you hit a golf ball or a baseball or something, how is that different from dropping a watermelon onto the ground? You got an idea, Sam?
Are you using the force to make it start moving instead of stop?
I gotcha. So that's in the neighborhood of what I'm looking for, but it's not all of it. You're warm. Yeah.
The impulse is changing when you follow through.
What do you mean by the impulse is changing? You're right, but
Like you're making it smaller or bigger than
okay, as opposed to the watermelon example,
you're changing the time. Like the force of the thing.
you're warm. Brady, you got an idea?
Can like does time depend more on force than force depends on time?
No, not exactly. Theoretically, they're inversely proportional as long as something, and that's what we got to figure out. You got an idea, Tim?
Does it have something to do with the golf ball starts at rest, and then we're adding momentum to it, and then with the watermelon, we're sort of losing momentum?
That's similar to what Sam was saying. So it's super close, but you guys are missing one important thing. So
Is it the impulse isn't like the value of the impulse isn't changing when the first one?
there you go. Say it again.
The value of the impulse.
This is important, you guys. A lot of you are talking. Listen. In the first one with the watermelon example,
The value of the impulse isn't changing, whereas in the second example it is.
right, in which case did the cart, have a larger change in momentum with the bungee cord or with the chain? Neither. They were the same. Because in all of those safety feature problems, there's a predetermined change in velocity. No matter what, that egg was going to stop. Right? Is that true when you hit a golf ball? Is the change in velocity predetermined? No, that's up to you. It depends on how you hit the ball, right? Do you see what I mean? The velocity is going to go from 0 to, you decide, right? Because it depends on how you hit it. Follow? So, that's why it's different. All right? And so the whole advantage then of following through is your force, which you get to decide, and your time, which you get to decide. The time is bigger when you follow through, giving you a bigger change in momentum. Follow? So, let's write it out. So, increasing the change in velocity. Why to follow through? Following through allows more time for the same force to act on the object. Do you know what I mean when I say that? Like, following through doesn't make you stronger. It's not like you suddenly swing harder because you've decided to follow through. All right, so following through allows more time for the same force to act on the object. This creates a larger, what? Impulse, change in momentum, right? just going to put impulse in parentheses. And therefore, except I'm going to write thus, because it's less letters, a larger what? Velocity's close. There's something slightly better than I want. Change in velocity. Does that make sense, you guys? Can you read my horrible writing? 4 points on a test. Are you ready for the 4 points? You can probably guess, right? More time. Same force. Larger change in momentum or impulse, and therefore larger change in velocity. 4 points. All right, tomorrow I will show you a quick demo of this, which will not involve breaking any eggs. And we'll watch a very quick video so you can see how airbags work and kind of get a visual for that. And then, hold on, the rest of the hour will be yours to work on 8.1b, which is weirdly challenging because it's really abstract. People always struggle with this assignment for whatever reason. All right? So due Monday will be that assignment and the next video. All right? Clear? Questions? Abstract.
I know what it is.